Hello everyone, welcome back to another episode of Marin Maths. Okay, всем привет, мои русские друзья. And well, here I'm going to show you something that I found really interesting in my differential equations class. That was like 2 lectures ago. We were talking about, the extra term that we would add into the differential equation for the force due to gravity or just to describe the motion of a falling object. And so, as you all know, that comes from Newton's second law, right? So the force is equal to the mass times acceleration. But if you want to, be more accurate in terms of, what actually happens, if you want to be more realistic, then you want to take into account the change in the velocity, right? Because the velocity might not be constant. Well, the acceleration is not constant, so that means that you have to describe it as a differential equation. So over here we have that, this is Newton's second law, but now we have mdv dt, which is, in other words, the acceleration is equal to the force due to gravity, m times g, right? And in this case, we're going to, make the approximation that g is 10 meters per second squared. And we're going to subtract a term, that actually accounts for the drag force, the force that is acted on the object by, the air, So that is going to be minus gamma times v. So it's proportional to v in this case because, well, it's just a small object. For larger objects, I believe that it's proportional to v squared. But for this problem, we're just going to talk about a method, for approximation. Let me erase this. For the approximation to the solutions of the equation that comes out of this differential equation. So once you solve this differential equation, given all of these initial values, all of these constants, then what you're going to do is you're going to get a velocity function v of t equals to minus 50t plus 50e to the negative t over 5. And now the question is, if you say, the object is dropped at 500 meters, right, initially. So over here, we have y0, right? y0 is 500 meters. Then, at what time, t, will the object, hit the ground? So that's the question. Also, they tell you the terminal velocity, but that just serves you to solve the differential equation, That's all. And so that way you can find your velocity function. But that's not what this video is about. This video is about the method that my professor used in order to approximate the answer to this problem, which I found it, really like, wow, like how could you come up with this? I mean, it's probably like sometimes mathematicians have a lot of time, so they play around with equations and graphs and they just find patterns, that's what it is. Because really, it works for like equations of this form when we solve this, So what we do is, because we know we have a velocity function, we just integrate, right, in order to make it a position function, because we are going to solve for the time given the position, initial position. So let's go ahead and integrate the velocity function. So integral of vt dt equals to the integral of minus 50t plus 50 e to the negative t over 5 dt. These are indefinite integrals. So over here we have the definition of the position function, x of t, is equal to, in this case we're going to have minus, I believe this t over here is not supposed, I remember from the problem it's not supposed to be there. So over here we're going to get minus 50t, so that's going to be minus 50t. And over here, when we integrate 50e to the negative t over 5, we use the chain rule, right? So first we, take the derivative of this, we divide by that, by the reciprocal, right? So we're just going to multiply by negative 5. So negative 5 times 50 is minus 250. E to the negative t over 5, right? Using the chain rule. Now, plus the initial value, or just plus the constant c, right? Let's just put c. And of course, we're going to use our initial value, which, in this case, occurs at t equals 0. So when t is 0, when t is 0, we know that c is going to be some value, right? and x equals going to be, xt is going to be 500 meters. So let's go ahead and solve that. So 500 meters, right? And then 0 times negative 50 is 0. E to the 0 is 1, so we're left with minus 250 plus c, which means that c is nothing but 750 meters. All right, that means that our position function, specific for this problem, is going to be minus 50t minus 250 e to the negative t over 5, and then c is 750, okay? Over here we can simplify this a little bit, to our convenience. We can divide all of this by 50, okay? Factor out the 50 if you want to say it like that, okay? And so we're going to get that this is x of t equals to 50, minus t, and then minus this over here is going to become 5, e to the negative t over 5, and then plus 15. Okay? Now, the problem is asking us to find at what time t does the object fall to the ground, right? When it hits the ground. So that means that we have to set our velocity, our position function equal to 0, and then we find the time, right? So let x of t be equal to 0, okay? And then we solve this function. Of course, the 50 doesn't matter because we're dividing by 50, and over here we got a 0. So we got something like this. We got t plus 5e to the negative t over 5 equals to 15. And here comes the trick, okay? This equation is very hard to solve with conventional methods. You cannot just, oh yeah, let's use the quadratic formula. No, it's not a quadratic function. It's an exponential function, with a linear term over here. So what my professor did, which is probably a method that, she came across during her career, was that she, takes advantage of, like equality of this graph. Because when you graph equations of this form, you're going to find out that it's going to fall from infinity, right? It's going to, let me erase this over here so I can show you how the graph looks like. Okay, so over here, the graph falls from positive infinity, okay? It falls to some value, negative value, right? Depending on what your equation is. And then it goes up in a linear way, right? So it falls exponentially, right? And then it goes up linearly, almost linearly. And it turns out, okay, I don't know why, but it turns out that this point over here, okay, is pretty close to this. It's pretty close. So basically what you're doing is you're guessing that that's the answer to this problem over here. Sometimes this might even go to the negative, but we're only interested, so suppose this is actually, yeah, in this specific problem, the other solution is negative, but of course we cannot have negative time, okay? So over here, we're going to find this point, assuming that, okay, it's very close to 15. So what happens is you're going to let t, okay, let t equals to some value, delta, plus 15, okay? And then in this case, we're going to let delta approach 0. How's that, right? Now, what's going to happen is, okay, we're going to substitute this, okay, expression for t into our original equation and then solve and see what happens. So let's see what happens, okay? Okay, so over here we have t plus 5e to the negative t over 5 equals 15. And of course, we know that t equals delta plus 15. So we have delta plus 15, okay, plus 5 e to the negative t over 5. So e to the negative delta, my deltas are kind of weird, plus 15, okay, divided by 5, and all of this equals to 15. Now look at that. This 15 and this 15 cancel out, right, when you subtract on both sides. And over here we can simplify this a little bit, so we have the delta plus 5 and then e to the negative delta over 5, right? Times e to the negative 15 over 5 is 3, so negative 3, right? Okay, all of that equals to 0. Now, because we're assuming that delta is going to approach 0, then that means that e to the negative delta over 5, right? That's just going to be, you know, pretty much, that's just going to be 1, right? E to the 0, what's e to the 0? 1. Okay, that just goes to 1. And we're left with delta, okay, is equal to negative 5 e to the negative 3. In other words, negative 5 over e to the 3, to the third power. And if you want to be, you know, if you don't want to be too rigorous, if you want to approximate this, you can say this is, you know, about minus 5 over e is about 3. So you could say 3 to the 3, which is 27. So 5/27, minus 5/27. We know delta already, right? And we know that initially we let t equals to delta plus 15. So in that case, we can say that t is going to be 15 minus 5 over 27. Okay? And that turns out to be something about, okay, 14.75. And you know, this value for t, and this is in seconds, is extremely close to the real answer, okay? The margin of error is very small, very small. So this is, you know, this is a really cool way to solve this equation, these kinds of equations. So when you come across, you know, these sort of problems, and let's say that you can use a calculator, I think this will be the best way to do it, right? And of course, you know, you can use your basic math skills to solve that. So I think, you know, it's amazing. It's an amazing method. It's really cool to go about solving this in these sorts of ways. And really, you know, the way they came up with this was just that, you know, they found out the behavior of this type of graphs. Once they know the patterns, okay, they can assume, you know, certain things to their convenience so that their approximations are very close. So usually that's what mathematics is about. It's about recognizing patterns, okay, between, you know, things related to your problem. So yeah, thanks for watching. And I'll keep posting videos soon so that you don't get bored. All right, see you soon. Пока.